Hello, welcome back to the session 3 of ML modeling and training. So the agenda for today's session is the ML modeling fundamentals, the core concepts behind the algorithms and their applications. How do we choose a particular algorithm? What is selection criteria? And some of the common ML algorithms. And then we'll look at Telnova churn solution, and then we'll see the what is a model training and what is the training essentials of model, and then we get into some a training process deep dive. Then after that we'll go to the SageMaker and then we train our model. So let's demystify this ML modeling for a moment. Think of ML modeling as hiring a super intelligent intern, one who reads through thousands of your past customer records, notice subtle behavioral patterns, and then helps you to make sure smarter future decisions. So for example, imagine you are running Telnova and you are got years of data. How often people call support, what plans they are on, how much data they use each month. These are our input features, our clues. Now we take all these clues and feed them to machine learning model, which you can think of as really advanced pattern matcher. It is not memorizing the data, it's learning general rules from it. Like customer who call support more than 4 times and are on month to month plan, they are 3 times more likely to churn. Then comes prediction. The model sees a new customer and says, based on everything I have seen before, there are 78% chance this person will churn in next 30 days. But the important part is we don't just want predictions, we want actions. That's where business comes in. If model flags a high risk customer, Telnova might instantly trigger a retention offer, maybe a discount or maybe an upgrade call. So that's where this ML modeling plays a key role, just not only predicting, it also giving you an actionable business insights. So choosing the right ML algorithm is not like choosing a right tool for surgery. So first we need to ask ourselves, what exactly I'm trying to predict? Is it yes or no? Whether a customer will churn, you are in a classification problem. If you are forecasting something, you are in a regression problem. Something like I want to forecast how many GBs you will consume, regression. Or maybe I just don't know what I'm predicting, but I want to understand hidden patterns in my data. Then we are in a clustering problem, right? So the next factor which influences data volume and variety, whether you are having millions of records, does it make sense to use something like a KNN there, which is might not scale with a large amount of data, but something like XGBoost might scale with millions of records of data. Other one is that whether how easy to interpret the model output, like how easy to explain the model outcome. Can I have the explainability in the model, like why a model made a decision, why a model rejected a loan to a particular customer, or so this is what important. I want to know like why something, the model take a decision. Another factor is that training speed and scalability. Whether you want something which is speed, quick for a quick prototype, maybe something like logistic regression can do in few minutes to seconds. It can run on your laptop also. Maybe, or you might have some kind of a deep learning model with the millions of records, and maybe you need to fire some GPUs for that. Then that's a different, that's a trade-off, whether you want to have a speed, whether you want how much time you are having, how much deadline you are, what is your deadlines you are working towards. So there is no right answer here. It all depends on your use case, the data you are having, your team, and your deadlines. So in the next few slides, we are going to walk through some common ML algorithms before we decide on what is that ML model algorithm we are going to choose for our Telnova's problem. So let's start with one of the most foundational algorithm in machine learning, which is logistic regression. So despite the name, this is not used for regression problem. It actually a classification algorithm and one of the best tools to reach for when you need fast predictions. So what does it do? Imagine you are looking at Telnova customer and trying to answer, will the person churn or will they stay? The logistic regression gives you the probability, a number between 0 and 1, that says there is 70% chance that this customer will churn or it doesn't churn. It doesn't just guess, it calculates this by assigning weights to features like support calls, data usage, tenure, and more. Then it squashes the results using something called sigmoid function, which curves everything into the nice smooth S shape you see on the right side of this, the slide. So the quick analogy or metaphor for this regression is like weighing scale. Each customer feature is weight you put on one side or other, more likely the churn versus more likely to stay, right? The model balances all these weights and says, based on everything I have seen, this person lands right here, just above 0.5. So they will classify them as likely to churn. Now, here is why it is being wisely used in business, because it is fast. You can see which features contribute the most. That means you have the visibility into why a model made certain decisions. And it is often first thing, we try just to get a baseline model. So, but it also has some limitations because it assumes a linear relationship between the features and predictions. So if a churn behavior depends on some non-linear interactions like combo of plan type, location, usage spike, it might miss those relationships. So still for use case like credit risk scoring or a fraud detection or churn predictions, where decisions have to be, where you have to make very fast decisions, you want to be able to explain your decisions, this particular ML algorithm, really works. So what are the common use cases? Anywhere you have a binary decision to make, yes or no, spam or non-spam, churn or stay, a fraud or non-fraud. This is where this algorithm will shine. Okay. So for example, customer churn predictions. This is kind of a go-to for telecom for over a decade. You want to do some create approvals because banks love it because it gives them a probability score and explain results critical for compliance. Why I decided not to approve the loan for a customer, I should be able to explain my decision. Something like a disease diagnosis. If doctor want to know whether a patient has a high or low risk based on symptom, this model gives you the 0 to 1 probability. Spam detection. Think of like a Gmail. Emails are scored by model like this based on their word formatting, sender metadata. So think of this logistic regression like a reliable, fast, and easily explainable model, right? One of the biggest things, as I told, is explainability. You can actually look at the model coefficients and say this particular feature increases churn risk by 30%. So that's what very important for business analyst. It also computationally efficient. You can train this on a CSV file in a Jupyter notebook and have results in seconds. Plus it gives you probabilities, not just a binary label, which is super useful when you want to rank customer by risk. Just instead of simply tagging them as it gives them, it gives you probabilities. And if you use techniques like a regularization, which I'm going to discuss in next coming sessions, it avoids overfitting also. So, and it works particularly well when the data is linearly separable, which happens more often than you would think with the well engineered features. But it also has got its own limitations, that it assumes that relationship between input and the output is linear. So what that means is that if a churn is caused by a combination of a plan type and billing cycle and customer age in some non-linear way, this regression might miss it entirely unless you engineer those interactions yourself. It is also sensitive to outliers. A few extreme values can throw off your coefficients badly. And with highly imbalanced data set where only 5% customer churn, it can get biased towards majority class. It will also just start predicting no churn for everyone to hit 95% accuracy. That sounds good, but it doesn't solve your business problem. So in summary, this is the go-to ML algorithm where you need speed, you want explainability, and your data is not too complex. But if you are dealing with noisy patterns, deep non-linear interactions, or imbalanced data set, it might be not the right solution. You might have to look something like a random forest or XGBoost. So now let's talk about the next ML algorithm, which is a decision trees. Think of decision trees like a flowchart you draw on a whiteboard to explain a business decision. At every box or a node, you are asking a yes or no question based on the feature. Something like, did the customer make more than 3 support calls last month? If yes, go to left. If no, go to right. This continues down the tree until you hit a leaf node which contains your final prediction, maybe churn yes or maybe no. Okay. So what is it technically? It is a supervised learning model, meaning it learns from the labeled data. It can handle both classification like churn predictions and regression like prediction customer lifetime value. So what is good thing about this decision tree is that it builds itself by splitting the data based on the features in a way that tries to maximize the similarity in the resulting branches. So how does it decide in the first place? So it uses something called Gini impurity or information gain, basically a math that tells it which feature divides many customers into cleanest and most informative groups. So if the feature called tenure less than 3 months gives a clean churn or no churn divide, it becomes the first split, the root of the tree. Each decision node asks one question, each branch is the answer, and each leaf is a prediction. For example, the node says is a plan type prepaid, and the branch could be S. Then it could check usage. The next node is usage is less than 5 GB. Then the leaf will be predict churn. So the beauty is that this is all very visual and easy to explain. Even a non-technical stakeholder can follow the logic of how this particular algorithm arrived at a decision. Now that we have explored how decision trees work, let's talk about when to use them and when to be cautious. So common use cases, decision trees really shine in real world problem like where transparency and explainability are essential. Something like customer segmentation. Marketing teams can literally draft paths to identify high to low value customers or churn prone segments. And then in case of fraud detections, the tree can flag suspicious transaction patterns, simple logic, high value plus overseas plus third transactions in the last 1 hour. So it's a red flag. In medical diagnosis, doctors often prefer model that they can reason with. If a patient's symptoms match certain pattern, the tree can guide treatment options. In loan approvals, banks can use trees to automate credit decisions while still providing audit friendly logic. And then in the predictive maintenance, for example, in manufacturing, trees can help determine when equipment is likely to fail based on operating patterns. So really any scenario where you have a lot of if else type of decision trail, this can help. So what makes this decision tree especially powerful is they are easy to interpret. You don't need to be a data scientist to read the decision path. That's a huge in the business. They'll work with both numbers and categories. Usage minutes, plan types, tenure, all handled without no transformations. They require minimal pre-processing, no need to scale or normalize. They can automatically capture interaction between features. If a churn happens and low data usage coincides with a short tenure, then the tree figures that out. And they are also robust to missing values and outliers. A small gaps won't break them, but they also have some limitations. Okay, they are prone to overfitting, especially if the tree grows too deep. That's why we apply tree pruning. They become too complex and messy. The logic might work for the training data but generalize poorly. Sometimes they're unstable. Even a small change in data can completely rebuild the tree in a different way. So if your data set is imbalanced, tree may ignore the minority class. And perhaps most importantly, they often underperform compared to ensemble methods like a random forest or XGBoost. So in short, trees are explainable, fast and low maintenance, but they can be brittle and may not give you the best predictive accuracy alone. That's why in practice you will often see them used as a building blocks in more advanced models. Let's not now talk about another ML algorithm which is random forest. One of the most popular and trusted machine learning algorithms out there. So imagine you are on a hiring panel with 100 interviews. Each person reviews a candidate independently using a slightly different set of questions. Once they have made the decisions, you don't rely on just one opinion. You take a majority vote. This is in essence a random forest, an ensemble of decision trees working together. So what is this ensemble approach? A random forest builds many decision trees, not just one. Each tree is trained on a slightly different view of the data. And the final prediction is maybe a combining output of all these trees. Why? Because just like you crowdsourcing opinion often leads to better decisions, combining multiple trees gives us more robust and accurate results. The next one is random sampling. Here is a clever part. Each tree doesn't see the same data or even all the features. We randomly sample the data, and then that's called bootstrapping, and also select a random subset of features for each tree split. This randomness makes sure that the tree don't all think alike, which makes the model more diverse and less prone to overfitting. So think of it like, just give an example, think of like having doctors slightly different specialization reviewing the same patient. Each brings a different perspective. So next one is that collective intelligence. So after training, every tree in the forest gives a prediction. If it's a classification problem like will this customer churn, then the forest takes a majority vote across all trees. If it is regression like predicting price, it averages a value, it takes average of all the values. So this is a collective decision, often outperforms any single tree by a wide margin. It's a wisdom of the crowd in action. One of the biggest issues with decision trees is they overfit easily. They can memorize the training data, which means they do great in training but fails in production. So random forests tackle this by combining trees with each make a different errors. When you average them out, these errors cancels each other out, and the result is much more stable and model. So to give you a real world example, imagine you are diagnosing a patient. So you bring in 10 doctors. Each doctor has got different specialization. One is a cardiologist, one is a nephrologist, one is urologist, like that. They have different specialization. Each doctor has got different piece of patient's history and slightly different scan. Rather than relying on one doctor, you collect all their opinions and go with the what is a common opinion among all of them. That's a random forest. It's a committee of experts, each with a biased lens, but together they make a remarkably a balanced prediction. First up, let's see some of the common use case for random forests, right? So one is the common use case, credit risk assessment. So bank uses random forest to evaluate a loan applicant. It takes into account dozens of features, income, employment history, payment behavior, and decide who is most likely to default. It's fast and handles messy data well. And hospital uses it to predict outcomes. For instance, will patient develop a complication post surgery? Since random forest handles missing data and outliers, it's perfect in the very unpredictable scenarios. And stock market forecasting. In finance, analysts love using random forest to go through high dimensional data. Think of hundreds of variables like past price, volume indicators, volume and other economic factors to forecast trends. And other one is that satellite image analysis. So if you want to do weather forecasting, you can use random forest to classify a land cover from satellite imagery such as a forest, desert, urban based on pixel values from different wavelengths. So the key advantages is that it has got a superior accuracy compared to a single decision tree. It is like comparing one person opinion to a collective wisdom of a panel. It tells you which features are matter the most in making predictions. That is really important when you're building explainable models, and it can handle high dimensional data efficiently. You got say 100 to 100 variables. It can easily handle those number of variables, the data, without any challenges. And other one is that the parallel processing capability. It can build the trees independently. So it works beautifully in a distributed or a cloud environment if you are using. And some of the limitations of this random forest is that If you're working with a small device or a low memory, random forest may be slow, especially with thousands of trees. And then you can't easily walk someone through the forest. For industries needing full transparency, like a legal or a healthcare audits, this might be a bit challenge and requires very careful hyperparameter tuning. How many trees, how deep, which feature to split. You will need cross validation and experimentation. And if you are having a data or the features which are highly correlated, then it struggles there. It might overweight some of them, leading to bias. So in summary, random forest silver bullet, no, not quite, but it is an incredibly versatile, powerful algorithm, and when tuned well, it often outperforms more complex models in real business scenarios. So next talk about next algorithm, which is k nearest neighbor, which is KNN. So this is one of the most simple, very and intuitive ML algorithm. You know, basically think about it like, if you're trying to decide whether to watch a movie, what do? You ask few friends who have similar taste. That's what KNN in action. You know, it is what we call an instance based learning algorithm. That means it doesn't try to learn model upfront. Instead, when new data point comes in, it goes back and checks the original data set to find the most similar examples, its neighbors, and then use them to make a decision. It also non-parametric, meaning it doesn't assume anything about how the data is distributed. That makes it incredibly flexible. So how it works? It works by breaking down it into 4 steps. One is you have to choose a value of k. This is the number of neighbors we want to consult. Maybe 3, maybe 5. We'll tune this based on our performance. Then we measure how our new data point is from every other point in the data set. Think of this like finding 5 closest restaurants around you using GPS. Then find the k nearest neighbors. We sort them and grab the top k closest neighbors, and then make a prediction. If it is classification problem, will this customer churn? We take a majority vote. If it regression problem, like how much data will they use, we take the average. So real world applications, now let's anchor this to our Telnova use case. Suppose we have a new customer and we want to know will they churn. We feed this in their features, support call frequency, data usage, plan type, and so on. KNN goes into our historical data, find the 5 customer most similar to this one, and check whether they churn. If most of them did, it predicts this new customer will also churn. Right? That's what is happening. You take one data point, try to find who are all similar. If they all belong to the churn category, you also assume that, okay, yeah, this customer is also going to churn. So as I told, if you want to think in more in the real world fashion, you just asking your 5 closest friends where to eat. If 3 of them say you eat Thai food, then that's probably your answer. It's local, it's context driven, and it is the one of the advantage, it is very simplicity. Now let's talk about the XGBoost, which is one of the most popular and common machine algorithm which you encounter in every day. Like if you go to any lot of Kaggle winning solutions or real world enterprise deployment, across industries, this is one of the most versatile model being used. How it works is that at its core, XGBoost uses something called gradient boosting, which means it builds an ensemble of trees sequentially. Each new tree is trained to correct the error made by the previous tree. The idea is instead of trying to fit everything at once, it learns a residual step by step, improving the prediction incrementally. So other advantages are high performance. Unlike traditional gradient boosting implementations, XGBoost is highly optimized. It's fast because it uses clever data structure and memory aware techniques. It handles missing values, parallel computations, and even sparse data natively. It is highly scalable. It can work on massive amount of data. That makes XGBoost an excellent fit, not just for almost every use case you encounter, you can do with XGBoost algorithm. Another advantage is regularization. One of the most standard feature of XGBoost is that it includes built-in regularization. We are going to talk about what is regularization L1, L2 in the next session. We are going deep dive into that. That's important because it helps to prevent overfitting, especially when you have a lot of features or a noisy data. So unlike other tree model that can grow over complex, XGBoost try to generalize better, which is what we want when deploying model production. So we are going to talk about how XGBoost works, step by step in the coming slides. But if we take our Telnova use case, we can use XGBoost here very efficiently because for chain prediction, and it consistently outperforms logistic regression or decision trees, right? So the summary, XGBoost is fast, accurate, scalable, and reliable, making it one of the most versatile tools, for any machine learning implementation. Now let's take a simple example and walk step by step how XGBoost works, because this is one of the most versatile ML algorithm. You might be using this everywhere, so it is very essential for to understand how it works internally. So we'll take a very simple data set and walk you step by step just to get a high level overview of how it actually works under the hood, right? So to step one, we have a input label data. We start with our data set. Let's say we are trying to predict the customer churn for Telnova. So we have a small table with just two features: support calls and data usage. Whether customer actually churned one or didn't churn is represented by 1 or 0. For example, one customer had 3 support calls and used 12.5 GB of data and they did churn. And another had 1 call and 20 GB of usage, they didn't churn. So this is our ground truth and this is a starting point. The data we will use to train and evaluate our model. So in step 2, XGBoost start with the base predictions, a simple guess before we build any tree. Say in classification problem like this, a common starting point is predict the average churn rate across all data points. In our case, 2 out of 4 customers churned. So the base prediction is 0.5 for everyone. So every customer starts with 50% predicted chance of churning. So in step 3, we compute the residuals. This is the core of gradient boosting, calculating the residuals, which are just error between what the model predicted and what actually happened. If the customer churn and predicted is 0.5, the error is 0.5. If they didn't churn and the error is then the error is minus 0.5. These residuals are what we want the next tree to correct. They are our learning signals. So after step 3, you have residuals, the errors made by your base model, which simply predict 0.5 for everyone. So instead of trying to predict churn again from scratch, the next step is to focus only on what was wrong in that base prediction, like residuals. So now your model job becomes train a decision tree to learn where and why we made a mistake. So in this case, you have residuals like support call residual like 0.51 minus 0.52 minus 0.54 plus 0.5. When you feed this in decision tree algorithm, it asks, can I split this data in a way that separates the positive residuals from the negative ones? So the tree might find when a support call is greater than 2, the residual tend to be 0.5. When support call less than 2, then it tend to be negative 0.5. Thus it learns simple rule. If support call is greater than 2, predict residual as plus 0.5, else as a negative 0.5. So this is a new tree job. It's not saying this person will churn, but rather you under predicted for this person by 0.5. So let me correct that. So in step 5, once the tree makes the predictions, we don't use it outright. Instead, we add a small fraction of its prediction to the original one. This is where the learning rate comes in. Think of it like a model saying, I will adjust a little bit at a time so I don't overreact. If the learning rate is 0.1, then the tree says plus 0.5. We add just 0.05 to the original prediction. So the updated predictions for customers become 0.55, 0.45, 0.45 and 0.55, slightly nudging the model in the right direction. Now in step 6, we recalculate the residuals based on the update predictions, build a new tree on those residuals and repeat. Each tree is correcting errors of the tree that came before. So over time, the sequence of corrections leads to more and more accurate predictions. In the final output in step number 7, after several iterations, the model prediction begins to converge. In our example, we might end up with churn probably like 0.87, 0.12, 0.15 and 0.91. So they aren't just guesses, they are refined stage by stage predictions that combine everything the model has learned through each round of boosting. So to summarize, XGBoost doesn't just build one big tree, it builds a series of small focused trees, each one learning from the mistakes of the last tree. And instead of overfitting like many complex models, it uses regularization and learning rate control to build smarter, more generalizable predictions. And that's why it works so well for structured problems in across industries. So now let's talk about what it really means to train a model. Imagine you are, teaching a student how to recognize if a customer is likely to cancel a subscription, what we call churn. You don't just hand them answer, you give them past examples like customer age, plan type, number of support calls, and tell them whether those customers actually churned or not, right? So the step 1 is the data, which is input of historical data. This is just giving the student a history book full of past cases, a giant table of real customer behavior and their outcomes. So at Telnova, for instance, we might feed the model, say 10,000 records of customers with label outcomes, churned or not churned. And step 2, a minimize loss function. Now comes the learning part. The algorithm tries to guess the outcome for each example. Initially, it is like a student making a random guess, but each time it's wrong, it learns from the mistakes. This is guided by the loss function. Think of it like you are trying to mark some errors when you're learning something. The bigger the error, you lose more marks. So our goal is reduce those marks, the minimize the loss as training continues. So if you have heard a term like a log loss or mean squared error, these are just ways to count how far we off from the truth. Next, you actually optimize the parameters. Now, just like you might teach a student different tricks to solve a problem faster, the algorithm fine tunes itself using methods like gradient descent or in our case boosting in XGBoost. It tweaks its internal knobs, what we call parameters, to make fewer mistakes in next round. So these knobs can be things like how deep a decision tree can grow or how aggressively it should correct itself with each new tree it adds. And then step 4 is a output of a trained model. Eventually, after seeing enough examples and minimizing enough errors, the algorithm graduates. It becomes a trained model like a well prepared assistant that can now look at new customers profile and say with pretty high confidence this person might churn or they will probably stay. So it is important to understand we are not just memorizing the data, we are learning patterns in the data. Just that's what say something like some for an example, some take is like a Netflix training model. It doesn't just memorize what you watched, it learns pattern like users who watched something like a 10 seasons in 1 week and then paused for 10 days are often cancelled. That insight, not just raw memory, it is what makes a model powerful. And that's essence of model training. We feed it experience, guide it with a measure of correctness and help it evolve into pattern spotting machine. Now that we understand what is XGBoost model, how it works step by step, let's talk about some of the hyperparameters. So what are hyperparameters? Let's understand that first. They are like a dials and levers on machine. Say if you're having a thermostat where if you adjust the temperature depending upon the way you adjust the fan speed, your room might become cool or hot. Similarly, the hyperparameters controls how your model might behave or predict eventually. So very important part of your model training. So if you ignore them, even the best algorithms can underperform. So the learning rate is one of the hyperparameters of the XGBoost. This is your pace of learning. To give an example, think like if you have a student learning maths and you push them too fast, they will get overwhelmed, and that's higher learning rate. But to go too slow and they might never reach mastery. In XGBoost, a small learning rate like 0.1 means the model takes a tiny careful steps. It needs more steps, or in our case more trees, to reach our goal, but it makes fewer mistakes along the way. Next one is max depth. Think of each decision tree like asking a series of yes or no questions. The deeper the tree, the more detail and questioning, but too deep and it starts to memorize the rather than generalize, like a student cramming the answer instead of understanding the concepts. So we often cap depth between 3 and 10. N estimators, this is how many trees we grow. More tree means more chance to fix previous errors. But remember, just like too many cooks can spoil the food, many trees can without proper tuning can lead to overfitting. Subsample, this is like testing your. Now let's deep dive into the what happens in the training of XGBoost. In step 1, as we saw an example, you start the base prediction. We begin with a very simple guess, often just an average churn rate across all customers. So if 30% of historical customers have churned, our initial prediction for everyone is 30%. It's like saying we don't know much yet. We'll start with the overall average. Then you compute gradient and Hessians. This is where it gets smart. We calculate how far each prediction is, that's a gradient. Then we measure how sensitive loss function is to changes, that's Hessian, a second derivative. Think of it like a, maybe to give an example like your Google map, right? It is recalculating the best route based on the current traffic. The gradient tells us which direction to move, and Hessian tells us how sharply turn. The gradient tells a model which direction to move to reduce error. The Hessian tells how steep or flat that path is, helping the model decide how big a step it should take. This is what makes XGBoost very precise than other boosting methods. So the next one is that, just to give another simple analogy, imagine you are hiking down a hill, right? The weather is not good, with low visibility, there's a lot of fog. The gradient is like feeling which way the ground slopes, which direction is downhill. The Hessian is like noticing how sharp or gradual the slope is. If it is too steep, you take small step. If it is gentle, you take a longer strides. Step number 3 is we fit a tree to residuals. Now we build a small decision tree, but not to predict churn directly. It is a trying to predict residual, the error from the previous round. So if your first guess for one customer was 0.3, but the true label is 1, they churn, the residual is 0.7. The tree tries to predict that 0.7 error. Imagine a tiny helper who comes in and then says, hey, I think you are too slow on this customer. Let me adjust that. Then in step 4, we apply regularization. To avoid overfitting, we apply penalties for overly complex trees. This is like pruning a garden. We cut back branches that don't add much value. This keeps the model general enough to perform well on new data. Next, in step 5, we update the predictions. We combine the old predictions with the new tree corrections scaled down by learning rate. So if the first tree predicted 0.7 residual, we might add, we might only add 10% of that. The learning rate is 0.1. The reason we do this is because boosting is a slow controlled correction. We want many small improvement, not big leaps. In step 6, we evaluate and repeat again. We check how well we are doing using area under the curve, area under the AUC, log loss or accuracy. If we are still improving, we go back to step 2 or do it again with the new residuals. If we stop improving or the validation error increases, we stop either due to convergence or early stopping. So this elegant loop continues, each tree learning from the last until we have built an ensemble of fine-tuned decision trees. That's how XGBoost achieves its accuracy, by correcting itself one tiny step at a time. So this is not only useful for chain predictions, this is useful for variety of cases like fraud detection, loan default, disease diagnosis predictions and everything. So the next one is modeling, like whatever we discussed just now about the modeling, the XGBoost model, the hyperparameter, everything we discussed. We are going to put this in action. It's just that we just need to use the SageMaker we'll see how we can train the model using SageMaker. First thing is that you have the SageMaker session. You get the SageMaker session. You do all this input required. There's SageMaker libraries. We have stored the bucket name, the prefix name, the Docker image name in the session in the previous notebooks. So we are going to read them again. So this is my bucket where I'm having. This is my prefix of the bucket. This is my Docker image which I'm going to use it to train my data using on XGBoost model. This is my train data, this is my validation data, right? So I'm going to, first thing is we are going to create a training input using the train data and validation data. We'll just see we are just printing here to see the config of this. These are my hyperparameter of max depth, subsample, number of rounds, ETA, gamma and everything. We discussed about each of these hyperparameters in the previous slide, like how they are going to impact the model training. This is a one small change I did to the existing code. As of the current code doesn't log all your experiments in MLflow. The reason we have an experiment is that when we train the model, sometimes we want to see like what happens if my model parameters like accuracy, F1 score or precision recall is going to change if I use depth of 5 versus 6 versus 4. Like I want to run different experiments, like how many number of rounds I want to run, what subsample, my gamma, I want to run different experiments. So for that, SageMaker Studio has got something called MLflow. The MLflow here. So you can create MLflow. You can start the MLflow server. Then it starts logging all your experiments you are doing into the MLflow. So this part of the code is not available in GitHub repos. I took this code and then made small changes to that to log all the experiments in the MLflow. So you can set the MLflow tracking URI here, and then once you do that, then you start creating the SageMaker estimator class, and you provide your batch job name, you provide the instance type name. Another thing is that by default you might not have the usage being enabled for you, so you can just go and then create the quota increase for that instance type, right? So once I start training, it will start training the model, and then it is going through all these different passes. Once the model training is over, you can see that how much, basically you can also see how much time training seconds it took, how many billable seconds. So this is kind of once this is a workbook code, right? But for example, what if you want to reuse this code and you want to make it in part of SageMaker pipeline, which we are going to discuss in the end. So we are creating some type of a reusable code so that whatever we have done so far, we can actually reuse in the SageMaker pipeline. So by the end of this one, the model is trained and ready to deploy. You can go back to your studio here. You can click on your experiments. It will log. I think I have stopped my. You can click on your models here. Now, any model which you have trained will be under deployable model. Now, this is a model I just trained. Of course, I trained. This is a model I trained. You can see that the model which I trained, the model location, and then the all other parameters of the model is there. You can also see that the model will be uploaded into the S3 bucket. So I can go here, XGBoost, I can click on output here, and then I can click on here. So in the output, the model is uploaded. Once this model is ready to deploy to an endpoint and ready for serving. So what we have done in this is that we have taken the data which is processed by the data wrangler, and we have used XGBoost model. Like we have a XGBoost container we have used and train the data what we have using that XGBoost model. In the next session, we are going to run some evaluations, and then we are going to see how the model is performing, whether the model is performing to the the way I am expecting. Based on that, we can make a decision whether we want to deploy this model or we want to retrain the model with additional data.